All right, welcome to 2-2 Day 2. We're going to look at normal distribution and their calculations. So first, we talked about the four-step process earlier. Now is actually where the time is that you need to implement it. So first, the first step is to state, and usually this is where you have your let statements, like let x equal whatever. The plan part is usually where you're going to draw a picture. You might draw a graph, something like that. Draw a picture. In our case, most of the time we're going to draw a picture of the distribution. And shade the area of interest under the curve. All right, so now let's look at the do part. This is where we usually perform our calculations. We might run tests depending upon what section we're in. This is also where we would standardize x. So this is where we would do like our z-scores. And then this is also where we would put the information from our calculator, or we might use calculator, or we might use table A. Right? The conclusion is where we're going to write our conclusion in the context of the problem. All right. So let's look at an example. Scores on the Wechsler Adult Intelligence Scale, which is a standard IQ test for 20 to 34 age group, are approximately normally distributed with a mean of 110 and a standard deviation of 25. For each part, follow the four-step process. So first thing we want to do is do our state part. So for the state part, we're going to do let x, identifier variable, I'm going to choose to use x, equal the IQ score of people aged (20 to 34). Right? One thing that I also like to do is to also identify what is given in the problem in the same place. So mu is 110 and sigma is equal to 25. So then our plan part, we're going to talk about kind of like what we want to find. Basically, we want to find the probability that x is less than 150, right? Because percentile means a location in the distribution from 0 to whatever the percentile or the score is. Then we'll want to draw a picture of the distribution. So the mean would go in the middle. 150 would be to the right of the mean. And we want less than, so we're going to shade behind 150. So hopefully our answer is more than half because we're past halfway across the curve. So we are going to now do the do part, which will be to find the z-score. So that'll be x, so 150 minus the mean, 110, divided by the standard deviation of 25. Put that in your calculator, you get 1.6. And then we're going to use the norm CDF function to get that the area is equal to 0.9452. So our conclusion is, is an IQ score of 150 is about the 95th percentile. All right, so now part B. What percent of people aged 20 to 34 have IQs between 125 and 150? We don't need to restate the x part because we already did that earlier. I don't need to rewrite what mean and sigma are, but what I am going to rewrite is the plan part. I'm going to write that I'm planning to find the area of the curve in between 125 and 150, right? So the probability of that area. Then I need to find the two z-scores. So I'm going to find the z-score of 125, which is equal to 125 minus 110 divided by 25, which is 0.6. We already found the z-score of 150 in part A, so that's 1.6. right? I am going to draw a picture of the curve again. I should have done that earlier. And 110 goes in the middle, 125 is to the right, 150 is to the right, so we're shading that area. We can see that our answer should probably be less than a half because we don't even have a full half of a curve shaded. So we do the normal CDF function, and the area that we find is 0.2195. That seems pretty reasonable. And we're going to write our conclusion. Therefore, about 22% of people aged 20 to 34 have IQs between 125 and 150. All right, part C says Mensa is an elite organization that admits as many members people who score in the top 2% of IQ tests. It says, what score would an individual have to earn to qualify for Mensa? So basically what we need to know is what this top 2% is. So if we don't need to do the let part again because we still have the same X. The plan, they told us that this time that the area is the top 2%. So really what we're trying to find is the z-score that goes with that area, and then ultimately the x that goes with that z-score. So the first part we're going to do is we're going to use the inverse norm, or use the back of our book to find the table. So you might want to draw a picture so that you understand what you're looking at. So the top 2% is this little tiny segment here, which means that from the beginning of the curve to right there would be 98% of it. So I'm going to inverse norm 0.98, and I'm going to get a z-score of 2.05, or I can look 0.98 up in the back of the book and find 2.05. Then I'm going to use the z-score to solve for x. So the mean is 110 divided by the standard deviation of 25. I'm going to use algebra to solve by x, so I'm going to multiply both sides by 25 and add 110. So I'm going to find that x is equal to 161.25. So my conclusion is, in an adult, I guess I could say an individual, but adult 20 to 34, age 20 to 34, would have to have an IQ score of at least 161.25 to qualify for Mensa. All right, so let's look at number 2. At some fast food restaurants, customers want a lid for their drinks. Get them from a large stack left near straws, napkins, and condiments. The lids are made with a small amount of flexibility so they can be stretched across the mouth of the cup. So when the lids are too small or too large, customers get very frustrated, especially if they end up spilling their drinks. One particular restaurant, the lids require a diameter between 3.95 and 4.05. So the mean is 3.98 and the standard deviation is 0.02. So what percentage of lids are too small? When it says show your method, that basically means use the 4-step rule, or the 4-step process. So we're going to start by letting x equal the diameter of the lid, since that's what the problem is talking about. I also like to write down what mean is, what mu is equal to 3.98, and sigma is equal to 0.02. Alright, so plan. We're going to find the probability that the diameter of the lid is less than 3.95. That would be too small. Draw a picture of the curve. Mean goes in the middle. 3.95 is a little bit to the left of that mean, and we want smaller than that, so it looks like it should be a little bit less than a half. So let's look at the z-score. The z-score is equal to 3.95 minus 3.98 divided by 0.02. So we put that in, we get negative 1.5. So it'll be quite a bit less than a half. So we're a full 1.5 standard deviations from the mean. So then we normal CDF it, we find the area. The area is equal to 0.6681. So move it to decimal place twice. And our conclusion is about 6.7% of the lids are too small. So what percent of lids are too big to fit? So the plan again, we don't have to do the let statement again because it's the same problem. The plan part would be what's the probability that x is greater than the biggest size, which is 4.05. We would want to make our curve. 3.98 would go in the middle. 4.05 is a couple standard deviations from the mean. So we want to do our z-score for 4.05. We would find out that 4.05 minus 3.98 divided by 0.02 is equal to a z-score of 3.5. So we do our norm CDF and we would find that the area is equal to 0.0002. Right? So now we're ready for our conclusion. There is only a 0.02% chance the lid is too large. So compare your answers A and B. Does it make sense for the manufacturers to try to make one of these values larger than the other? Alright, so if more lids were too large, then there might be more spills, right? You'd put your lid on, you'd think it fit, and maybe you'd lift it up by the lid and it'd spill everywhere. If it was too small, you probably would throw it away and get another one. So that's kind of what they're banking on here. So does it make sense? Yes. It makes sense. The smaller lids are more likely to be noticed by the consumer. And they'll throw them away. And get a new one. Right, if your lid doesn't fit on, then you're most likely to just put that one in the trash and pick another one. If it's too big, you might not have noticed that it wasn't quite on there enough, and then your drink might spill like later in your car when you try to pick it up. So hopefully that makes sense. Alright, so let's look at this problem, number 3. It goes right along with number 2. This time we're going to see which would be better, if we should adjust the mean or adjust the standard deviation. So we're going to look at a standard deviation. So we're talking about too small. Remember that the lower bound value for that was 3.95. And we're talking about if the area was 1%. So we don't need to identify x again. So we'll just go to the plan part. So I'm going to draw a picture to start off with the plan part. If we're talking about 1%, 1% is a tiny itty bitty piece of this curve. And we want to know what the z-score is at that curve, and then find the x that goes with that z-score. So this is when you use inverse norm. So we'll put in our calculator inverse norm 0.01, and we'll find out what the z-score is, which should be negative 2.33. Right? Then we're going to use the z-score to find the value of x. So the z-score is equal to, or sorry, not the value x, the mean. The lower bound is 3.95. We want to find out what mean would go with that. And the standard deviation we decided would stay the same. So then again, we just multiply both sides by 0.02. We're going to subtract 3.95 from both sides and then change the signs. So you should get the mean is approximately, it rounds to 4. So 4 inches. So what happened was we said that it couldn't be that the average mean now is going to be 4, but that makes sure that we have a really, really small percent that's too small. But does that increase our big size, right? And then do we have a likelihood of making more lids that are too big for the cups? So if the mean diameter stays at mu equals 3.98, so this time we'll keep the mean the same, what value does the standard deviation result in less than 1% of the lids are too small? So again, remember that the lower bound for too small from the previous problem was 3.95. The mean is going to stay the same. And now what we're looking for is what will our new standard deviation be. So again, it's the same picture as above, so I'm not going to restate the state part. I'm not going to restate the plan part because it's the same problem as above. The z-score is going to stay the same because we have the same area. What is going to change though is the equation. So the z-score is equal to, we know we're talking about the lower bound. We know we're talking about the mean of 3.8. What we don't know is the standard deviation. So we're going to simplify the top, which would be negative 2.33 equals negative 0.03 over sigma. So multiply both sides by sigma and divide by negative 2.33, and we should get the standard deviation is approximately 0.013 inches. So the question is, which of the two options in A and B do you think is preferable? Justify your answer. Be sure to consider the effects of these changes on the 1% of lids that are too large to fit. So we looked at the 1% of lids that are too small. And they're also reminding us to look at the larger side as well. So would we want to keep the standard deviation the same and increase the mean? Or do we want to keep the mean the same and decrease the standard deviation? So which one seems better? So obviously, hopefully you're saying that you should choose B. The standard deviation will decrease in part B, which will decrease the variability of the cup sizes, which means that both of them will be closer to the mean, right? And there won't have as much deviation from the mean. It will not decrease the number of lids that are too big, but it will reduce the number of lids that are too small. Right, so we're going to choose B. Let's write that down. The standard deviation will decrease which will decrease the variability. So they'll all kind of hover closer to the mean. It will not increase the number of too big lids, but it will decrease the too smalls, right? The ones that are too small, right? So basically, if the mean gets bigger, like in A, the number of lids, small lids, will be reduced, but will also increase the number of lids that are too big, which is what that increasing the mean to 4 did, is we just said, well, okay, we can have a lot more bigger lids. So that's why A was not a good choice. All right, so we'll talk a little bit more tomorrow in class and do our assignment tomorrow in class as well.